Hi, this is Mike Lopez, and in this video, let's see if we can demystify sinusoids and phase angles. Okay, notice here in black, f of x equals sine x. Okay, the black waveform is this guy here, of course, just in case you haven't got the best quality screen. And you can see this sine wave starts at 0, peaks positively, negatively, and goes back to 0 here, and then it just repeats over and over and over, and that's what a sine wave does. And what we say is a sine wave completes one full cycle when it's completed 2 pi radians. And if you remember what radians are all about, so essentially we start here, we work all the way around the circle, 1 revolution, and we've covered 2 pi radians. Okay, obviously, or you know, at school you used to say 360 degrees to go all the way around. If you get to this point here, you would have done 180 degrees from the starting point, or if you like, in trigonometric measure, pi radians to get to that point there. Okay, so that's what's happened there. So this thing is gone, although I'm going to change it to red just to emphasize it. To go from there to there, you've gone halfway through one complete cycle, and so there you have 180 degrees is equivalent to pi radians. Okay, and then you just double those two figures to achieve 2 pi radians, or 360 degrees. In terms of this idea of phase angle, so we're looking at this thing here and this thing here. When we have a leading phase angle, so plus means leading, what that means then is, if you look at the blue waveform there, okay, that's this one, it leads what the original waveform was by this amount, pi by 4. So what do we mean by pi by 4? Pi by 4, well, we know what pi is. Pi is 180. So what's 180 divided by 4? Yep, it's 45 degrees. Okay, so we have a 45 degree lead here. And when we say lead, a waveform will lead another if it peaks before the other one. Okay, so in terms of if this was drawn on the oscilloscope, the whole thing would be moving this way, coming towards you, and if that's you there, what comes to you first is this one here. Okay, so the blue wave hits you first, so that peaks first, so that has the leading phase. And conversely, down the bottom here, this one, we've got this minus sign, and so that's denoted by this green one here, not lags, so it takes a bit longer for the green wave to come to you. So if you like, here's you sitting here, and all this stuff is coming your way. Okay, so blue hits you first, then the black, and then the green. So that's what we mean by lagging and leading phase angle. Here we can see what looks a bit like a similar case, but we have different numbers involved here. Okay, if we go back to that previous one, look, we had 1 and minus 1 as the amplitudes, okay, which is standard on a calculator. Okay, if you were to go on a calculator and type sine of 90 in degrees mode, of course, sine 90, it should give you 1. And if you were to type the sine of 270, you'd be asking this height here, and sine 270 should give you -1 on your calculator. But we don't have to restrict ourselves to sine waves just of magnitude 1 and -1. We can have any magnitude we like. So here we've chosen 8. So that magnitude corresponds to this number here. Okay, or any of these, in fact, because these are just, of course, as we've just explained, separated by different phase angles. So the first 8 corresponds to the peak value here. This sine term here tells you, well, it's a sinusoidal shape, so it goes up and down like this, like a sinusoid does. This 2 pi is standard. Forget the star, that's just used in the graph simulator to make the simulation happen. 2 times pi, so we're looking at a function which is, we can call it supply voltage equals 8, which is the peak value. It's a sine wave. Here we put in frequency information, and here we put in frequency. Here we have the phase information. Okay, and you'll see this very commonly throughout engineering. And I suppose what we'd like to do is to be able to find for t, possibly. Okay, so how are you going to shift all that around and find for t, and produce a correct answer in terms of picoseconds, nanoseconds, microseconds, whatever it might be. Okay, well, the first thing we need to know is what's the value for frequency? Why don't we use frequency equals 2 megahertz? Now, you know what 2 megahertz means? It means 2 million hertz, or 2 times 10 to the 6 hertz. Okay, it's not just 2, don't just forget the capital M. 2 million. Okay, let's have the supply voltage Vs be 4 volts, and we're going to find for t. In other words, I want t equals blah blah blah, or in this case, an actual time. So the first point in time where t is 4. Okay, now if you look at these graphs here, you've got minus pi by 8 there, so it's the green graph. You're looking at the green graph. When does the green graph go to 4 initially? Well, here's 4 there. So we're looking at that point in time there. What is that point in time? That's our question. Okay, so we're going to look at this whole thing, and we're going to start transposing. We've done transposition before a few times now on these videos, so divide both sides by 8. We start with Vs over 8 equals to sine 2 pi ft minus pi by 8. Okay, move on a step further, save some paper. How about taking the sine minus 1 of both sides? In that case, that sign is going to disappear, so we're going to have sine minus 1 of Vs over 8 equals 2 pi ft minus pi by 8. Okay. Let's change colour again, make it easier to follow. And then we're looking for, well, we want to isolate this t here. That's what we're interested in. So it might be a good idea to move the minus pi by 8 over to the left, and then it becomes plus pi by 8. So then we're going to have sine minus 1 Vs over 8, close those brackets, plus pi by 8 equals, well, what's left over on the right there was just 2 pi ft. Okay, and if you divide both sides, change color, divide both sides by 2 pi ft, so that thing there is going to go on there. So we should have something conveniently t equals sine minus 1 vs over 8 plus pi by 8 all over 2 pi times the frequency. Okay, I'm being very careful with frequency. We can look again at this and express it as t equals sine minus 1 and start putting in these numbers. So we know what Vs is. Vs is 4 divided by 8, close brackets, plus pi by 8 all over 2 pi f. 2 pi times f is frequency, and we set up here frequency was 2 megahertz, which is 2 times 10 to the 6. So it's that times 2 times 10 to the power 6. Okay, we can simplify this. Let's change colour again, and then we're looking at t equals 0.524. Now this 0.524 has come about because I've got my calculator in radians mode, because I noticed there's a pi here. Okay, so when you're using trig and you've got pi's involved, always put your calculator in radians mode. So sine minus 1 of 0.5 in radians mode should give you 0.524. And then you work out what pi by 8 is, of course, and you should get 0.393-ish. That's just rounded all over 4 pi times 1 times 10 to the 6. Probably easier way for you to put it in on your calculator. You notice the 4's appeared because we've got this 2 times this 2 here. Okay, and we should have an answer. T equals 72.97 nanoseconds, which is equivalent to 72.97 times 10 to the minus 9 seconds. Okay, so I encourage you to go back, have a look at the graph simulator, and see if you can get this thing simulated in the graph simulator, and it'll give you a better feel for the whole problem and the ideas behind sinusoids and phase angles.